Alright everyone, so tonight I'd like to talk about textual reduction semantics versus closure creating interpreters. In assignment A3, we're going to be creating a closure creating interpreter. And I think a lot of people probably rightfully had the question of, well, why do we even need closures to begin with? And a point that I'd really like to get home in this lecture is that you really don't. But there's a good reason we have them. And the main reason is efficiency. We can write an interpreter based totally off textual reduction semantics, which is to say the kinds of things we did on the board by manipulating terms by hand. We can write an interpreter like that completely. It's just going to be really, really slow. And we're going to illustrate that today. And we're going to do that some benchmarking of this style of interpreter against a more conventional closure creating interpreter. So let's dig in by starting with just the plain lambda calculus. So the lambda calculus consists of three different forms. We've got variables, we've got lambda abstractions, and we've got applications. All right, nested under lambda abstractions are other lambda calculus terms, and we have some E0 applied to E1 for applications. And nothing else is a lambda calculus term. All right, so for example, we've got lambda x applied to lambda y. If you recall from class, we had this rule beta, which is basically the heart of computation if we're going to do computation on the board, right? And what does beta reduction say? Well, beta reduction essentially says that you perform computation by plugging in arguments. So you do things like, let's say, if you recall from a high school math class or something, f of x equals x times 2. If you want to calculate f of 2, you can say 2 times 2, which then you can rewrite to 4. All right, so in the lambda calculus, the rule that allows us to perform this computation is called the beta rule. And in that case, we'll take the body of the function that's being executed once we have a lambda to apply, and then we'll take it and we will replace that body, the variable being the argument, we'll replace that with the argument given to the function. So because lambda yy is the argument here, we're going to replace x with lambda yy, and then we'll get back just lambda yy. All right? So I'm going to write a simple version of the heart of this algorithm, which is substitution. Now in class we talked about two different kinds of substitution. We talked about naive substitution, and we talked about capture avoiding substitution. Now I'm going to write a version of basically naive substitution, and in this lecture we're going to assume that all the terms we're going to use are going to be alphatized. And what I mean by that is that we aren't going to have any variables clashing or anything like that. So we're never going to have terms like lambda x, where this version of x, it's a little bit hard to know. You have to look and say, well, it really goes with this binder rather than this one out here. We can make this a little bit more syntactically apparent by rewriting all of the variables that lambdas bind to be totally unique occurrences of variables. And that process is called alphatization. We can either do that by alpha converting the term so that all the different variable definitions are all different, or we can just generate terms correctly. But the upshot is that as long as we're dealing with these alphatized terms so that no variables are the same, we can define substitution a little bit more simply. And so I'm going to make that simplification right here. If you're interested in thinking about how we can use capture avoiding substitution to do this, you totally can. The exercise E5 goes over that, and I'm happy to talk with you about it on Slack. So how do we substitute? So the definition of substitution says, within the term E0, substitute x for E1. All right, so we have three different possibilities. Either E0 is a symbol, right, because a lambda could be a symbol, or it's a lambda abstraction, or it's an application. All right? So there are these three different possibilities. So in the first case, if it's a symbol, we have to consider whether that symbol is equal to the thing we're trying to replace. So if we see some symbol y, and we know that y is equal to x, well then we know this is the thing we're trying to replace, and we should just give back e1. Otherwise, if it's not equal to x, then we should just leave that alone. This would be the case when I say replace y, within y, replace x by lambda z. Well, you would just want this to be y, because y is not equal to x. Okay, application is pretty simple. You just substitute within both of the subterms. And then lambdas, you basically substitute within the body, or when you get to a case when you have a y, if x is equal to y, you just stop because you don't have to do any more substitution. All right, so now we're going to get to our first interpreter. We can define an interpreter that's called interp_subst. This interpreter is going to use substitution to actually perform computation. So here's how we're going to do it. Let's say that I have a variable x. How do I compute what that variable is? Well, x is basically, we can't really do anything with it, right? So what we're going to do is we're just going to return that variable itself. All right? Now, what about if I have a lambda? So if I have a lambda x e0, well, I can't really do anything with this either. So I'm just going to return back lambda x e0. The real heart of the algorithm is this one right here. Let's say that I have some e0 applied to e1. What do I do? Well, the simple scenario is when I have something like this. Lambda x, e body, and then some e1. Well, what I'm going to do is I have kind of a few different options. If I want to use a call by value reduction strategy, the first thing I really want to do is I want to take and interpret this e1 down to some value, v, which is either x or some lambda. Because if we remember, call by value says that we need to basically fully perform applications until we get down to some value. The first thing that we're going to do is we're going to fully evaluate e0, then we're going to fully evaluate e1, and then we're going to plug the value we get for e1 into e0. That's what call by value tells us we have to do. All right, so let's do that. What we're going to do is we're going to say interp_subst e0. This says evaluate e0 to a value, which is either going to be some variable x or some lambda. Really, it's actually just going to be a lambda, except for the case when that variable x is a free variable. And if we assume the term is fully closed, then what that means is that we're only ever going to end up with something that's a lambda here. Now, because this e0 is in the function position, we know that it had better be a function that can be applied to a value. Because, for example, it wouldn't make any sense to have something like, let's say we had the term y applied to lambda z. Well, that wouldn't be something we could really compute with. We need something that more looks like lambda xx applied to lambda z. All right? So we're going to assume that the computation for interp_subst e0, in doing that, we're saying go ahead and fully evaluate e0 down to a value. All right, and we'll talk again about why that's important in a second. But once we get that value, then we're going to assume it looks like lambda with some argument x and some e body. And then we're going to call interp_subst, and we're going to substitute e body x for, and now here we're also going to call interp_subst e1. All right, and so what we're doing here is we're saying evaluate E1 down to some other value. All right? And then substitute in the body the variable x for the result of computing E1. And this is because we want a call by value interpretation. In fact, it turns out that if I leave off that subst function, I just write E1 here, I get the call by name interpretation. We'll maybe experiment with that if I have time towards the end of the video. All right. So let's just define, oops, messed this up a little bit. I think it's all right. All right, good. Okay. So let's do interp subst lambda xx lambda y, and we get lambda y. All right? What about if I do lambda xx applied to lambda y? Sorry, lambda x applied to x, and then lambda y. We still get lambda y. And I'll let you see that is by I'll let you see why that is by just doing lambda calculus style reduction using the beta rule, like you would have to do on the exam. All right, what about a little bit more complicated term? What about something like this? Lambda xx applied to lambda y, all of that applied to lambda z. Well, I get lambda z. But look here. Let's say I hadn't actually substituted. I hadn't actually interpreted E0. Let's say that I just did E0 right here instead of interp subst E0. We're going to see there's going to be a problem. Well, I'm going to see here E0, what was it? Well, let's print it out. We're going to use a pretty print, E0. Let's just run that. All right. And it's going to tell me, all right, so I'm trying to match something that's an application. Well, I can't really match anything against that because it's not a lambda yet. And so what I'm saying is that if I have an E0, if it's some more complex form than a lambda, I might have to do a bunch of work to actually figure out what the function is, right? And this is just like in racket if I do something, well, I mean, this is basically a racket term, right? Or this is literally a racket term, as long as I don't put the quote there. That works, except procedure doesn't tell me very much. We're going to see why that is in a few more minutes. All right, but the upshot is I need to interpret that. All right, and I'm also going to point out a pretty cool little interesting tidbit here, which is let's do interp subst, or actually let's do omega. Let's define the omega term as lambda x applied to x, and then lambda y applied to y. You should recognize this term by now. If I actually compute this term, it won't terminate. So let's try that. Interp subst omega. All right, so let's see what happens. All right, but of course it doesn't work. All right, so we know that omega doesn't work. It's not going to work in racket, and it's also not going to work in our interpreter. So let's try making a small addition to it. So let's copy this and say define omega as argument. Now what we're going to do is we're going to take the omega term, and before it we're going to put lambda z, lambda a. We're going to apply that to the whole term. So look at what we're doing. We're going to take this omega term, which doesn't terminate, and then we're going to apply it to this lambda, which then drops it on the ground. See how z is never used within this term? Now it's a lot of work, right? But or actually, I guess not that much work, just 2 or 3 steps of beta. But you can reduce this to a term where you just never see this this omega term used. And that's going to happen if you use a call by name reduction strategy. So let's look at how we evaluate this in Racket. So if you evaluate this in Racket, it doesn't terminate. But if you use a call by name evaluation strategy, it does. So first, let's run our interpreter. Interp subst. Doesn't terminate there, but we can make a pretty easy substitution to our interpreter. If we just do this, now we get an interpreter that does call by name instead of call by value. All right, so let's try running that. And then we just get lambda AA. All right? So we can very easily modify our little interpreter to be either call by value or call by name. I'm going to put it back to call by value because that's the conventional one that we're going to keep talking about a lot in this class. All right? All right, so now what I want to cover is testing our interpreter. So my claim in the first part of the video is that the substitution-based interpreter is just slow. It's way too slow to actually use for basically anything. And the reason is, if we look at the interpreter, every time we perform beta reduction, we're going to substitute within this E body X for the result of interpreting E1. So what that means is we're going to be doing a whole bunch of crawling through these E body terms and calling out to the substitution procedure, which is going to have to reach arbitrarily far down into a term. So let's consider some term like this. Let's say I've got something like lambda x, lambda y, lambda z, and then x. And then something like that. And then let's do something like apply that to x. And then this. We'll apply this to y. And then this whole thing we'll apply to lambda. Let's say a. Well, when I do this substitution, and I substitute in this body right here, I substitute x for this term, I'm going to have to reach all the way down into this term right here and substitute all these different occurrences of x. And in fact, in general, I could have a huge number of those x's. All right, so substitution is just going to be doing an incredible amount of work. It turns out it's actually going to add a polynomial, I guess maybe even exponential factor. I haven't really thought it through very much, but it's really going to add a whole bunch of work to every single beta reduction we're going to do. And we're going to see precisely why. So I've got this little piece of code here, gen term, which is going to accept a size parameter, k, and it's going to give me a term that looks basically something like this. It's going to stack a whole bunch of lambdas, lambda x, and then it's going to do lambda y, and then it's going to do lambda z, and then it's going to do z, and then it's going to apply all of that to y, and it's going to take this and apply that to x, and then it's going to take that and apply it all to some outer term, lambda a. Except it's going to make that size parameter k, that's going to be the number of lambdas out here stacked up. So what this means is it's going to give me a term that's some size in k. All right, so it's going to give me a term where the term size is linear in k. All right, so if I do gen term of 3, it's going to give me this stack of 3 different lambdas. Now, I'm going to let you read this code and figure it out if you'd really like to. Frankly, you don't have to fully understand it if you don't want to. It's just some term that's going to help me figure out how to generate lambdas that I'm going to use to benchmark the interpreter. So that's what we're going to do. And then I have a little piece of code called time thunk and test. And what test is going to do is it's going to generate 10 different terms of varying sizes. So it's going to basically, this piece of code is going to map over 1, 2, 3, 4 all the way up to 10. And it's going to generate terms of size 1,000, 2,000, 3,000, 4,000, and 5,000. And then it's going to let me make a plot where I can say, if I take a term of size 1,000, that's going to take some amount of time t0. If I take a term of size 2,000, that's going to give me a term of that's going to take some time t1, and so on and so forth up to 10,000. That's going to be t10, or I guess t9 actually. All right, and so we're just going to look and see how, observe how that growth, how that interpreter, how it scales as I turn up the term size linearly. All right, and remember, just because I'm turning up the term size linearly doesn't actually mean I'm performing a linear number of beta reductions necessarily. But in this case, I think it basically does something either linear or I guess polynomial. But just let's just look at it and see what happens. So I have this little thing, display outputs test input subst right here. I'll let you read over that at some point if you like. I'm going to switch over now to looking at the bash terminal right here. All right. All right, and now we're running that. And let's just see how long it takes to run. All right, and remember this is running terms from size 1,000 up to size 10,000. All right, so it's going to take a while. I needed to run this with term sizes that were large enough that you would be able to see the general trend, because the upshot here is going to be pretty surprising. We're going to get actually surprisingly large runtimes for this substitution-based interpreter. So that's taking a little bit too long to run. Let's cut that off, and let's go back to Dr. Racket. Let's tune down some of these parameters. So instead of running it on sizes 1,000, 2,000, let's just run it on maybe 100, 200, 300, up to 1,000, because that's taking too long. Okay, so here we go. So I can see it at size 100, it takes 11 milliseconds, 200 takes 64, 300 takes 118, 400, 291, and I can see it's pretty computationally expensive actually. When I have a size of term of size 1,000, it takes 1,300 milliseconds. Now you might ask yourself, why does it take why does it take less time to run on size 1,000 than it does on 900? Well, the real answer is that this stuff varies a little bit due to things like garbage collection and the way the interpreter is running under the hood. So if we bump up this term size, if we bump up this multiplier here to, let's say, 300, try rerunning it again, we'll eventually get outputs that are a general trend that's pretty stable and is always monotonically increasing. But you have to make the term sizes pretty large before you see that general trend, which is why I was trying to run it with something pretty big to begin with. All right, so let's see. All right, this is taking a little bit longer. Probably polynomial, more amount of work. All right, and we've got our results. So if we start with 300, we get 156. We eventually get 10,699. All right, so let's just keep that in mind as we go to the next phase. All right, so in the last part, we've seen that our textual reduction substitution-based interpreter for the Lambda calculus works for some fairly large programs. In fact, we've got it running here with this term of 3,000 in size, or something proportional to 3,000. And it takes about 10 seconds to run, 10,699 milliseconds. But that's actually pretty slow. And in fact, the reason it's slow is because every time when we perform substitution, we're actually having to traverse this entire term. So every time when I perform beta reduction, I have to explicitly perform a substitution. And so that means when I'm performing a beta reduction on some big term, I end up having to basically copy and go through the entire term, which is going to be really, really slow. If I have a term of size n and I want to perform some beta reduction, well, I have to copy over that entire term, use that substitution operator, and then completely traverse through the entire term and then go all the way back up to reassemble it. That's what the substitution operator is going to do. Because if we look here at what the definition of substitution is, if I give it some really big term in which I want to substitute x for some e1, I have to dig arbitrarily deep through x and go all the way down to the leaves, or basically the symbols and application forms. All right? So instead of doing that, I'm going to do something a little bit different instead. I'm going to perform substitution in sort of a lazy way. And the way that I'm going to do that is that I'm going to add this thing called an environment. Now, an environment is going to allow us to look up variables on demand. So when I get to a variable like x, instead of just literally giving back the value x, I'm going to assume that the variable x is stored in this environment. So this is interp clo, because I'm going to build closures in this interpreter. We'll see why we need closures in a second. Okay, so let's say I have something like this variable x here. Well, now I have an environment. The job of this environment maps variables to values. So what I'm going to do is I'm going to take href env and give it back, and then give x. So I'm going to look up x in env. And then I need to do one other pretty tricky thing here. So in my in my textual reduction semantic style interpreter, when I got to a lambda, what I did was I just gave that lambda back. I just gave the entire lambda back as the answer. Unfortunately, I'm not really going to be able to do that here. So let's look what happens like something like this. Let's say that I've got lambda x, lambda y, x. So let's say I take this term and I apply that to lambda z, z. So what should the output of this term be? Well, in the textual reduction semantic style interpreter, if I use textual reduction, I would actually reduce that to lambda y, and then I would substitute for x with lambda z, z. All right, so then I would get lambda y, lambda z, z. But the whole point of writing the interpreter in this new style is that I don't want to have to perform explicit substitution, because performing substitution is incredibly slow. We found that it's going to take 10 seconds to process this term of size 3,000. All right? So it's just way too slow to actually perform that. So instead of saying, well, your answer is lambda y with lambda z, z right here, what we're actually going to do is we're going to say it's lambda y z in an environment which is a hash that's going to say z is going to go to lambda z, x. Oh, excuse me. This should be x. and then x should go to lambda z, z. But it turns out that's not quite right either, because this lambda zz also has an environment associated with it. All right, and it turns out that this environment that it's going to be associated with is in this case the empty environment, because when I start interpreting this top level term right here, no variables are set. Like if I just tell you to look at just this entire term right here, no variables are defined yet, right? I haven't defined any variables. Only when I start interpreting the body right here do I define x to be equal to this. So at every step along the way, what I'm going to do is I'm going to track an environment that's going to map variables to values. And then when I return a lambda, I need to return the lambda alongside the environment that goes with that lambda. And the pair of those two things together is actually called a closure. So I'm going to call this a closure of this lambda right here. And then simply the empty hash, which is going to be the top level environment. All right, and that way, if somebody actually tries to apply this function right here, what they're going to do is they're going to switch to this body x, but they're going to switch back to this environment right here, so that eventually when they look up x, they'll get back lambda zz and this empty hash. All right, so it's going to come together really, really nicely. We're going to have to see how it works. So basically the upshot is, whenever I return a lambda, I really need to return a closure of that lambda, e, alongside the current environment. And that's because if I'm about to return a lambda, well, I know all of the free variables in that lambda need to be closed over by the current environment. That's why it's called a closure, because it takes a term like lambda yx, x is free, this definition of x comes from the enclosing environment, from the environment where x was defined. All right? All right, so whenever I hand you a lambda, I need to tell you that when you apply it, you need to switch back to the environment that held the variables that were being used for that lambda. All right, so it's a really nice trick. It just means because we're going to interpret variables in this lazy way, we're going to need to remember whenever I build a closure or whenever I return a lambda, there are going to be some free variables in that. And so I'm also going to return the environment that's going to give me the definition of those free variables. And the pair of those two things is conventionally called a closure. And the reason it's called a closure, again, is because it's taking what variables are otherwise free and closing over them. It's making the term closed. If you remember, this term right here, this variable is free. So if I were to give x a definition, I would be closing over it or closing the term. And this environment env right here has to maintain a binding for x, assuming this had come from a valid term. All right? So the upshot is the result of this entire application right here should be a closure of lambda yx in a setting where x is equal to lambda zz, and really a closure lambda zz alongside the empty environment. And that's what we're going to see. So let's play around with that in a few minutes. All right, so next we have to define the application case. All right, so let's look at what's going to happen. So now we're going to say match interp clo e0, but now we have an extra parameter. So what environment are we going to use to interpret e0? Well, all of the variables in e0 should get their binding information from the current environment, right? Because if I have something like, let's consider that I have a term like x, y, and my current environment says something like, well, x maps to some closure, and y maps to some other closure. Well, I need to look up E0 or x from this current environment right here. And I can do that by just passing in E and V to interp clo. All right? And then what I'm going to get back right here is going to be a closure of a lambda, because I need to assume that the closure has this lambda right here, and then some other closure environment. All right? And then, instead of calling interp subst, I'm going to call interp clo, and I'm going to interpret the term E body, but I need some environment to put right here. So what's that environment going to be? Well, there's a crucial observation, which is that a closure packs a lambda with the environment that's going to give binding information to free variables within that lambda. So let's say that there's some free variable, like let's say we get a closure of lambda x y, and our environment is going to say hash y to the empty environment, or the closure of let's say closure of lambda x x and the empty environment. Okay, well in that case, what we need to do is we need to remember, well, the binding information for y is actually in this closure, or sorry, is in this environment right here. And that's because exactly when we created the closure, when we return a lambda, all of the variables from right here have to be looked up in this environment right here. All right? And so the upshot of all of that is that when we interpret this closure right here, we're going to switch back to clo env. All right? It's almost like if you're calling a method on an object or something like that, you switch back to the sort of field variables or instance variables corresponding to that object. In fact, it's exactly like that, because objects are the sort of object-oriented analog of closures. If you've ever done any amount of Java programming, or I guess really JavaScript programming as well, though JavaScript does have proper closures. All right? And then this is going to be expected a closure. All right. But there's one mistake here. So this clo env is going to give definitions to the free variables within eBody. But it's not going to give a definition for x. That's a fresh variable that we're just introducing, right? That's the formal parameter that corresponds to this lambda that was returned right here. So we have to do one last step, which is to update this closures environment, x, with the corresponding value that we get back from interpreting our argument. So we're going to call interp clo e1, again using the current environment, and then we'll have our answer. And if we want to make this a little bit more explicit, we could use a let statement. So we could say let arg value be and this is going to say compute the argument e1 down to a value argv. And then we're going to update update the closures environment to bind X. All right, and that will now give us our answer, and we'll have everything we need. All right, so let's see some examples of how this interpreter works. Oops. Oh shoot, let me turn off the testing code, because otherwise we're going to waste a bunch of time here. Okay, here we go. So let's do interp clo of lambda x x. I get a closure of lambda x x with the empty hash. And that's because there's no free variables in lambda x x. Okay, what about interp clo lambda x x applied to lambda x lambda y y? Okay, well that just gives me lambda y y. And this is because when I get down here and actually perform the application of this to this, well, I still don't have any free variables left. All right, so let's try something more interesting. Let's try lambda x, lambda y x, and then we'll perform lambda z z. Okay, so now we have something interesting. Now we have a closure. So we say apply this to this. That's going to give us lambda y x. Now in the textual substitution interpreter, we would have actually performed the substitution in this term to fully substitute x, which would have caused us to do quite a bit of work. And so that would make this textual substitution interpreter very slow. Instead of doing that, the interpreter is just going to sort of shallowly thread through lambda y x, but it's going to pass along this closure to bind the argument x right here, so that we know when we interpret this term, lambda y x, we need to do so in an environment that sets x to the closure of lambda z z. Now why do we have this other closure here? Well, because consider, we could keep applying x. And when we apply x, it could have some stuff inside of it, right? This environment, or sorry, this term right here might have some stuff inside of it that can actually grow arbitrarily large. Right, so let's take this really big term, let's do gen term of 10. I don't actually know what we're going to get here. So let's do interp clo of gen term 10. And see, we just end up with lambda zz because we go through this big string of lambdas, but we eventually end up with lambda zz from the top level. So I might be able to massage this a little bit to get us something more interesting. So let's do gen other term, see if I can do this by inspection. So maybe let's try that. No, that's not going to work. So I think I'm not going to be able to come up with an obviously awesome example that's going to generate a really huge closure. But maybe I'll let you think about how to do that offline. And if you're having trouble coming up with one, feel free to talk to me about it on Slack, and I can think about it some more. I'd like to be able to come up with some cool examples that show how you can generate really, really huge closures. But I think we've sort of done a lot of this so far. So let's kind of cut to the end and do kind of the big demonstration. So let's just pull back a little bit and go back to testing and benchmarking the substitution-based interpreter. Now remember, this interpretation, this interp subst, is going to run the substitution-based interpreter, which is going to do the exact same thing as the closure converting interpreter, except instead of producing closures, it's going to explicitly substitute terms, doing what we were doing on the board. And so let's see how long that takes to actually execute. So it's going to do a whole bunch of computation. It's polynomial in size, because it's doing a whole bunch of beta reductions, but on each beta reduction it's doing a substitution. So it ends up being some polynomial. I don't know if it's quadratic or really what the base is. Or sorry, the exponent is. Okay, so we can see we get 300 all the way up to 3000 takes 9,543 milliseconds, so roughly 10 seconds. All right. So now for the big reveal. Instead of using interp subst, let's use interp. Let's blow this away because I didn't actually need this. That's the code that I just rewrote. Interp clo. Boom. All right. It's wicked fast. So this is doing the exact same thing as the regular interpreter, the substitution-based interpreter, except here it's doing it much faster. In fact, we can go back and do it all the way up to many bigger terms if we want. It's going to be walking through the term in a linear number of steps rather than a quadratic number. And so it's going to take us a lot bigger terms to cause the interpreter to blow up. We should see roughly linear performance. I'm not sure why it's jumping all over the place, actually. My guess is that it has to do something with garbage collection, just because you're dealing with pretty large terms here. All these terms are all pretty large already, so they're going to be doing quite a bit of garbage collection going through them. But that's basically the upshot, is that when we write our closure converting interpreter, instead of having to do a quadratic or a polynomial traversal through the term, because at each step when we perform beta reduction we're also going to perform substitution, instead a closure converting interpreter is going to produce closures. And what that means is that when we actually perform beta reduction right here, instead of doing an explicit substitution, all we're doing is performing a single hash set. And that hash set, performing hash set in Racket, is basically constant time. It's really something more like, well, it is basically constant time. It's using a hash array mapped try, which does give constant time bounds. It's a pretty big constant, but something on the order of 10 or 20 operations, something like that. All right, so it's way, way faster. Sorry, 10 or 20. Well, it's kind of complicated to explain. I'll go over the way that these hash array map tries work maybe at the end of class, because it's a particularly beautiful data structure that really shows how you can get nice high-performance persistent maps in Racket, which are essentially what you need for writing these interpreters. But as long as this hash set operation is constant time, you get much, much better performance. And so what that means is that we can handle basically humongous terms that would just totally fall apart if we tried to do them in the textual term rewriting interpreter, right? We can try, instead of doing interp clo here, we can do interp subst. And I think this one will spin all day, right? It was exploding even on terms that were 1/100th of the size, right? And causing, I think, if we cut this down 1/100th of the size, now I think it still takes like 10 or 20 seconds. Okay. All right, so that's lecture for today. The upshot is that when we use a closure converting interpreter, we do the minimum amount of work possible in terms of substitution because we're performing substitution lazily. So closures are doing the exact same thing at some sort of very high level as just textual reduction semantics, but they're doing it in a much, much more efficient way by doing the substitution lazily. All right, so thanks so much for listening.